Welcome back once again to this lectures on distribution theory. So, in the last couple of lectures we are trying to give lot of motivational examples, and at the end of it what we are trying to give is a understanding of a function in a new form, in the sense that of an association. So, instead of viewing function as a point wise association, you try to view the function as a association from a class of functions. It is a kind of a linear function which we are going to see. We soon see that this will lead to a large number of new objects precisely called the distributions, and that is what we are going to discuss. So, we will be seeing in the whole process a large number of examples as motivational. Of course, once the examples are given, we have to get into the real mathematical aspects of it. So, try to not only listen these examples, you try to work out all the examples, which some of them I will be working out here, many of the other examples will be through exercises, but it is important that you work out the examples to grasp this new idea. For example, so let me get into the last page of what we have discussed. In the last page, so you see you have an association here as function. We have given that instead of that associate in this way. Okay. So, you can have something like this. Okay. So, you have that one. So, you associate that f and going to f. Okay. So, you have to try to understand that phi going to integral of phi, and this is more relevant. The importance of that association will soon come when you deal with the differentiable function. So, we start with a function f which is C1. So, you see which is a C1 function, and thus an association as a point wise association, you have x going to f prime of x. But now that we view as an operator, namely phi going to integral of a to b f prime of phi b. But then using the integration, since phi has compact support, do an integration by, and phi is also smooth, do an integration by parts, and then the boundary terms do not come, and you have this one. So, the pointwise approximation x going to f prime of x can be recovered from this one, you see, when f that one. So, this association can be defined even for non-differentiable function. It is enough to have a locally integrable function. So, that leads to immediately to define a different notion of derivative, in the sense that for non-differentiable functions. So, let me get into that a weak derivative. Okay. We will define it for more generally, but let us so let f be locally integrable, f be locally integrable, define df. We denote by the weak notion of derivative of df. Df will be a mapping, it will act on function. So, phi going to, that is what we are going to do, that phi going to df of phi, that is nothing but minus integral of a to b f phi prime. The question is that whether this is also the, so the one of the question is, does there exists g locally integrable such that minus integral of f phi prime is same as integral of g phi for all phi in d omega, for all phi, which is c infinity, this is a c infinity and compact support. These are the two properties we co-back support. I will tell you more remarks about such things. So, you see can do that. If so, if such a G exists, we get rather df can be identified with G, maybe the almost everywhere sense whatever it is. You see can do that. But the problem is that such a G may not exist. Problem or issue, such a G may not exist. We will see an example immediately, may not exist. But so, we have a new way of understanding a notion of a derivative for non-differentiable functions. Okay. And this is what we are going to now quickly see in a more general sense. So, let us start with a couple of examples. So, very simple examples we will do. As I said, we will see more and more examples. Example, consider this function f x equal to modulus of x in minus 1 to 1. Okay. So, that means this is your function 0 here, you have this one and you have this. This is at minus 1, this is at 1 mod x is continuous, but not C1. Okay. So, let me go to the other color, maybe more better. So, it is not C1. So, what is your weak derivative? So, your df is weak derivative, These concepts are new, as I said, it may take time, but you try to get used to it. df of phi is equal to integral minus 1 to 1 modulus of x phi prime of x dx. This is by definition. You look at the definition. This is the definition. Okay. So, it is mod x into phi prime of x. The problem is that you cannot do an integration by parts at this stage, because mod x is not a C1 function. But then this is C1 except at the origin. So, I can write this equal to minus 1 to 0 and then I can write from 0 to 1. So, on minus 1 to 1 mod x is minus x, minus of minus x is you get x phi prime of x, and here you get minus, because minus of minus. So, you will have minus of x, because mod x is plus, and with this minus you get x phi prime of x. In minus 1 to 0 and 0 to 1 x is differentiable. So, you can integrate by parts, but keep it in mind phi has compact support in minus 1 to 1. So, we have phi at minus 1 equal to phi at 1 is equal to 0, but phi at 0 need not be 0. So, you can do an integration by parts. Once you do an integration by parts, you get minus integral minus 1 to 0, differentiate x, you get phi of x dx, and then you have the boundary terms. You have to do integration, because you do not have phi does not have compact support in minus 1 to 0, it has compact support only in 0 to 1, 0. And then you do an integration by parts, there you get plus integral 0 to 1 phi x dx and plus minus x phi at 0 to 1. Now, look at this term, the second term. On the second term, phi at minus 1 is 0, but x is 0, phi at 0 is need not be 0, but then x is 0, So, this goes away because of the x is 0 that factor. Similarly, phi at 1 is 0, but x is 0 at 0, phi of 0 not necessarily 0. So, this term is also goes to 0. Now, with this I can write here integral minus 1 to 0, minus 1 to 1 I can write phi x d g of x. I will define what is g of x, phi of x, where g of x is equal to minus 1 if x belongs to minus 1 to 0 and plus 1 if x belongs to 0 to 1. Of course, it is defined almost everywhere, that is enough. At 0 it does not matter, whatever value you give at 0, the integral will be 0. So, this is what exactly we are looking for this example. So, in this example there is no trouble. So, this implies my weak derivative same of df that is equal to g, that is same as f prime x is keep note that f x equal to so this is a remark you have to know, f prime is x f prime is of x is equal to f prime the log minus 1 if x is in minus 1 to 0, same thing. So, it is plus 1 x at 0 to 1. F prime of 0 is not defined, that is the only thing, is not defined. So, it is a classical derivative almost everywhere. In other words, f prime equal to g, that is equivalent to f prime, the classical derivative in the almost everywhere sense except that the origin. So, you are identifying your df equal to g in the classical sense, but the situation is not the same when you get into more difficult problem. So, we will go to another example. Okay. Here I use a function what I call a Heaviside function. This you probably know already, otherwise Heaviside function, that is h of x equal to 0 if x less than 0, equal to 1 if x is greater than or equal to 0. So, that means you have a discontinuous function, this is defined on R, and so you have a disk function here, this one open here, the at 1 you have 1. So, a discontinuity otherwise. So, here also h is discontinuous, h is discontinuous, but h prime x is almost every h prime equal to 0 for all x not equal to 0. You see, h prime is not defined, h prime of 0 is not defined. Again, the difference between the previous function thing and this example, the previous function was continuous, though h prime f prime was not defined at the origin. Here also h prime x is almost everywhere, but except at the origin, but there is a discontinuity. You see this discontinuity. So, let us compute my dh. So, let us compute dh, compute dh. So, you have to write down dh at phi, that is equal to 0 to infinity, because at minus infinity to 0 is 0 and there it is 1, and you have minus phi prime of x dx. And now recall, phi has compact support, therefore, phi at minus infinity if you want to call it. This is a bit of an absurd notation because phi is not defined. So, but you can say that phi equal to 0 after a compact set. Okay, 0. That means phi equal to 0 outside a compact interval, outside say sum outside from minus m to m, you can say if you want. That is the most better way of telling it is 0. Now, do an integration by parts, this exactly gives you, because this is 1 here. So, the integration by part, that is 0, and then only the boundary terms will remain, and at infinity it is 0. So, you get exactly phi 0. Okay. So, your association is phi going to phi 0. See? And that is your DH. DH is phi 0. So, I will leave it as an exercise here, maybe in one of the exercise we will be do it. There does not exist any locally integrable G such that DH is equal of phi DH of phi that is equal to phi 0, that is equal to integral of minus infinity to infinity G phi. Only if it is such a G exists, you can identify this association as G. So, this is a new object now, giving a new association which cannot be realized, from a function, You see, that is the advantage when you are looking at it, and these are the realization. This is precisely, if you recall, this is precisely your delta. I have motivated you. This is precisely your delta phi. So, this exercise is already given to you. So, the delta which Dirac was visualizing or envisaging was something like that. So, of course, you need a more interpretation of that one. Okay. So, now let us in this view remark or comment, okay, remark. You can also call it comment. Let us recall again, you are already studied the nullifiers. Recall nullifiers. Okay, rho epsilon, and you have seen that in some sense this is close to delta, not fully. This is a question, of course. What you have seen is that rho epsilon of x go to 0 for all x not equal to 0. So, this is first condition, all right. But then you also want the second condition, 1 equal to integral of rho epsilon of x dx. Where does this will go? That is the thing where you want to understand, and that is where we have failed. So, here is another. So, this course is full of small exercises which will make your subject in a better way. So, the now exercise in the step, let us view, exercise will come soon, let us view rho epsilon as an association, Okay. What is the meaning? So, instead of viewing x going to rho epsilon of x, view, this is what I want to see, view rho epsilon as an association that is phi going to integral of rho epsilon of x phi of x dx. So, here is an association x going to f or rho epsilon of x, and you have seen that if everything is smooth, this is same. When you have a this is what yesterday in the previous class we had seen that this is somewhat equivalent, that is what we are trying to say. If you have that one, you can view a function in terms of that, but we are not able to pass to the limits here. You get a pointwise limit on the left side, but you do not get any integral thing on this one. So, the exercise is that show that. So, let me write in that one, show that maybe it is done, it is already in your assignment in the preliminaries. This goes to where the phi 0. So, this requires some study. This is your exercise. You have to work it out, this going to that one. This happens for all phi C infinity with compact support. So, under this association at the association level, you are able to pass to this limit exactly what you want to do it. Of course, you have to view that integral part, that I will soon tell you something about that. And the problem is that when you have a rho epsilon as a pointwise, then view it as a association, or that association you are able to pass, and that is more closer to like your Dirac delta, but unfortunately the Dirac delta is we are not able to recover it from a function g. That is what we have seen it in the previous example. So, something else is happening here, and we want to understand these kind of objects thing here. Okay. So, what are the other things I want to tell a few more things. All right. Yeah. So, this is typically at this level it is going to phi 0. So, let me make one more comment before going here. So, we are having functions. So, the functions we are working from this all motivation, the association phi have is C infinity. So, this is a kind of a remark at this stage. Phi is infinity, and it also has compact support. Okay. If you realize the previous example, the compact support actually leads to localization. You can get local values if the function localization. So, the compact support is used, that is how we got motivated. So, if you have a phi, if you act on any small open set, it will recover there. So, you can in fact, if f is smooth, by taking averages you can actually get that function value if the function value is defined. So, the compactness is used for localization, and what is smoothness is used from the previous example. Smoothness, if you look at the previous example of the derivative, maybe the previous to that one. Yes, when you calculate the derivative here, you see the derivative here. Since mod x is not differentiable, that derivative we are not able to do integration by parts, the derivative is coming here. So, if you want to deal with the functions which are more and more irregular, you need more and more smoothness on phi. And so, the smoothness is basically to deal with more and more more irregular functions. So, you are actually demanding putting in your test function class more irregular functions. Okay. So, these are the two important property you need to have it in your association, and that was enough to recover your function. So, with that we need to then, so this automatically forced to consider, we need to consider the space which we have introduced in our thing. Basically this is Cc of omega infinity. So, d omega is associated with a topology. So, you need to consider set of all functions which is C infinity of omega, where you call it omega. We are all studied this in detail in our preliminaries, is R n open, okay, such that support of phi compact. Okay. So, this is what you have done. So, what we have done in the preliminaries associated a topology. A topology that is called convergence. So, we have, but most of our work in this course we need to only understand the convergence. So, let me just recall not the entire topology, we recall the convergence for the sake of completeness. We recall convergence in d omega, which we have already studied, but let me take it. We say, because of the linearity, we say phi n belongs to d omega converges to 0. It is enough to consider convergence to 0. You can also talk about phi n converges to phi, means equivalent to say that phi n minus phi converges to 0. If this is very important, there exists a compact set K, okay, contained in omega such that, so the existence of compact set is a part of the definition of the convergence. That is what you have to, this is something probably you may not know much in functional analysis. In the first course on functional analysis, most of the places you may not learn that one. So, because the topology should inherit all the properties of that space, then only that kind of spaces will be complete. So, if you do not incorporate certain properties, then that property will not be recovered in the limit and leading to incompleteness, such that phi n, support of phi n. So, let me write it in a color. Support of phi n, support of phi n contained in K, that is okay. So, the second part, this is the first part, support of d power alpha of phi n converges to 0 uniformly. It is enough to say uniformly, but because of the fixed compact set, it uniform in every, it is whether you say that it converges to uniformly on K or omega, does not matter, because the support is already there. So, the d power alpha of phi n support is also in K, and it is immaterial whether in some book if you see that uniformly on K or uniformly on omega, both are correct. But when you go to C infinity of omega, that is a difference. So, in general there is a difference when you say uniformly in omega and uniformly in K, but in this case it does not matter because of the first condition. This should happen for all multi integers, alpha. Okay. So, then you say that you have seen in detail again. So, I just recalled this definition. So, you can see various references like probably some of them K7, you see Rund. There are many, anyway we will be giving a list of references. So, there are many books if you want to see this convergence to study. Okay. All right. So, we will go to the next page. Should I start something more or not? Yeah, one more remark and then probably I will stop it after that one remark, and then we will go to distribution. Remark is that, so d omega, you have to be careful, is not it is as a set, it is C c infinity of omega, but d omega notation is used when C c infinity of omega is given by the above topology. So, C c infinity d omega notation is used to represent C c infinity of omega, represent C c infinity of omega with the above topology, with the above topology. Okay. So, or convergence. Okay. So, with that what we will do is a kind of we will start with the distribution definition. Okay. So, we will start exactly in the next class, but let me make. Okay. So, the distribution, so given a locally integrable function, a locally integrable f, you have view it as a phi to integral of f of phi. We will see the proof later, which is more remarks later. So, which is a mapping from d omega to r. So, immediately, so the idea is to give a definition of a such an association independent of a particular integrable function. So, the idea is to give an axiomatic definition, give an axiomatic definition of such a mapping, by looking into the properties of an association, looking into the properties, So, what are the properties? We are looking into two typical properties. One, linearity, such an association is linear. The second thing, the fundamental properties. So, basically we are sanitizing that association by imposing some continuity. We need that, since d omega is already embedded with the topology, we want this to be this association to be continuous. So, essentially we are looking at, so this is a way, so you have two properties of linearity and continuity, and you do not require any function to define an association, and that is going. So, basically you are looking at the dual of d omega. So, we will stop there and continue now the formal definition of a distribution, which is almost motivated with a lot of examples and how to. So, it was quite natural. So, the most difficult part in this theory basically was identifying the correct topology, correct convergence, which is what given by the Lorentz Schwartz. Eventually view all these objects as the dual of d omega. As remarked in our introductory preliminaries, so whenever you are introducing a space, you need to have that space a dual. The dual should not be empty, and this is provided by the locally convex topology. So, the topology introduced in d omega is a, but if a metrizable topology is possible, the dual need not be non-empty. Okay, but locally convex topology gives you non-empty dual. So, we want to get a large number of elements, that is precisely different. Thank you. So, we will continue.